Hello everyone. In today's lecture, we are going to discuss about Hooke's law. Now, before discussing about Hooke's law or stating or defining it, let me tell you the concepts that which we have learned in the previous lectures, that is stress and strain. I hope you remember that, right? So stress is nothing but force per unit area, and strain, that is change in ratio of change in configuration to original configuration, right? So according to Hooke's law, the if the deforming force, if the deforming force is of small magnitude, and the deformation in the body, if it is small, then the stress produced in the body, would be proportional to the strain in the body. I hope you got that. So let's write that. What is the statement? For small deformation, for small deformation, the stress produced in the body is proportional to the strain in the body, So I hope you got the statement or the law. That is, according to Hooke's law, for small deformation, the stress produced in the body is proportional to the strain in the body. Now, as we have already seen, whenever there is a force, let's consider the longitudinal force or the normal force acting, acting normally to the area of cross section or along the length of the body, that is either tensile or compressive. In that case, the stress produced in the body is proportional to the strain produced in the body, because as we know, whenever there is a stress, that is force per unit area, longitudinally, there would be either elongation or compression. So whenever there is elongation or compression, there is strain, that is change in length upon original length. So this stress would be proportional to the strain. I hope you got that, right? So the stress, if I write it mathematically, stress is directly proportional to strain. Stress and strain both are, stress is proportional to strain in a body when the deformation is small, and of course for small deformation you need to apply small deforming force or small magnitude of deforming force. I hope that is clear. Now let's see one example based on it so that your understanding is more clear. Now, as I said, according to Hooke's law, stress is directly proportional to strain. Now let's see one example. So basically, when I say stress is proportional to strain, I mean all types of stress and strain. That is, when I write stress proportional to strain, stress proportional to strain, that means I mean longitudinal stress is directly proportional to longitudinal strain, that is tensile stress or compressive stress directly proportional to tensile strain or compressive strain. And of course, shear stress is directly proportional to shear strain, volume stress is directly proportional to volume strain. I hope you got that, right? So now, as this picture is shown over here, as you can see, this is the example of longitudinal stress proportional to longitudinal strain. So over here, either you provide tension stress or compression stress, tension stress or compression stress, both are of longitudinal or normal stress. So in that case, there is strain also, as you can see. So over here positive strain, over here negative strain, as you can see, because strain is nothing but, or longitudinal strain or tensile strain or compressive strain is nothing but the ratio of change in length and original length. So over here it is positive, over here negative. So over here, as you can see, more the stress, more is the strain. More the stress, more is the strain. I mean, whenever the stress in the body is more, there would be more strain. That is the meaning of stress proportional to strain. Okay, lesser the stress, lesser the strain. How? Because for stress you need to apply longitudinal or normal forces over here, as you can see, right? So more longitudinal or more normal force, more is the strain, that is more would be the increase in the length. So more increase in the length means strain would be more, because as we have already seen, stress is equals to force per unit area, isn't it? And strain equals to delta L by L. Okay, I am talking about longitudinal strain, that is either tensile or compressive. So as you can see, if I apply more force, then the more restoring force would be there. More restoring force means more stress. So more force means more elongation or more compression would be there. So delta L would be more. So if delta L is more, strain is more. So that's why stress is directly proportional to strain. I hope that is clear to you. So now if stress is proportional to strain, okay, removing the proportionality sign, we write stress equals to one proportionally constant E, okay, into strain. One proportionally constant E into strain. What is this proportionally constant over here? This proportionally constant E over here is called as modulus of elasticity. What is that? Modulus of elasticity. Modulus of elasticity. And this modulus of elasticity depends upon the nature of material. Okay, nature of material means what type of material is used to make the body. Okay, and it depends on the temperature of the body, and it is nothing but stress upon strain. What is that? Stress upon strain. E equals to stress upon strain. Okay, so modulus of elasticity is nothing but the ratio of stress and strain. Clear? And its unit would be Newton per meter square. Newton per meter square. Why? Because strain doesn't have unit any, it is unitless or dimensionless, and stress has the unit same as pressure, that is Newton per meter square or Pascal. Okay, I hope that is clear to you. Now this modulus of elasticity, as I said, it depends on nature of material which is used to make the body. Okay, nature of material. Also it depends on temperature, and it does not depend on dimension. It does not depend on dimensions of the body, length, breadth, height, area of cross section, okay, anything. It only depends on nature of material and on temperature, and its unit is nothing but same as stress, that is Newton per meter square. Okay, or we can sometimes write Pascal also, not a problem. Now what I was saying is, if this E, that is the proportionality constant, is modulus of elasticity, there are three types of modulus of elasticity. Let's see, as we have already studied about different types of strain and stress and strain. So over here, when I say stress is directly proportional to strain, I mean longitudinal stress is directly proportional to longitudinal strain, shear stress directly proportional to shear strain, volume stress directly proportional to volume strain. So all these three will have three different modulus of elasticity, because when as I have written over here, E equals to stress upon strain. So there are three types of stress, three types of strain. So ratio of three types of stress and three types of strain would be nothing but three types of modulus of elasticity. Let's see what are those. Now as I said, there are three types of modulus of elasticity based on three types of strain and three types of stress. I mean three types of stress and three types of strain. So as we know, modulus of elasticity E is equals to stress upon strain, right? So first type based on type of stress and strain, that is Young's modulus of elasticity. What is that? Young's modulus of elasticity, that is longitudinal stress upon longitudinal strain. Right? So the first kind, that is Y, we denote it by Y, and that is nothing but Young's modulus. What is that? Young's modulus of elasticity. Young's modulus of elasticity, that is nothing but longitudinal stress upon longitudinal strain. Second type, based on type of stress and strain, it is called as shear modulus of elasticity or modulus of rigidity, we call it. What is that? Modulus of rigidity or shear modulus of elasticity, that is shear stress upon shear strain. Okay. What is this? Shear modulus of elasticity or modulus of rigidity, we call it. Modulus of rigidity. Okay. Now, the third kind, based on the type of stress and strain, that is nothing but volume stress upon volume strain, and this is called as bulk modulus. What is that? Bulk modulus, or you can call it as volume modulus of elasticity also. Okay. So, bulk modulus of elasticity, volume stress upon volume strain. All right. What is this? Bulk modulus of elasticity. Clear? So, based on the type of stress and strain, there are three types of modulus of elasticity. First one is Young's modulus of elasticity, that is for longitudinal stress and longitudinal strain. Second one is modulus of rigidity or shear modulus, that is represented by G, that is nothing but shear stress upon shear strain. And the third one, the bulk modulus B, which is nothing but volume stress upon volume strain. I hope that is clear to you, right? Now, these two, that is shear stress upon shear strain, that is our modulus of rigidity, and bulk modulus, you will be studying in higher class in detail, but as of now we will just discuss about Young's modulus of elasticity, right? So, as we have seen all the three types, that is Young's modulus, modulus of rigidity, and bulk modulus. So, we will be focusing on Young's modulus only as of now, and the other two you will be studying in higher classes in detail. So, Young's modulus of elasticity, why? That is nothing but longitudinal stress upon longitudinal strain. So, longitudinal stress upon longitudinal strain. So, what is longitudinal stress? That is the restoring force acting normally along the length per unit area of cross section upon what is longitudinal strain? Delta L upon L, isn't it? So, from here what can we write? The Young's modulus of elasticity is nothing but F into L upon delta L into A. Okay. So, we can simply write it as FL upon A delta L, and its unit is nothing but Newton per meter square. As we have already seen, the SI unit for modulus of elasticity is same as stress, that is Newton per meter square or Pascal. Okay. So, now that was all about our Hooke's law, that is stress directly proportional to strain. Okay. I hope that is clear to you. Thank you.